Alright, this video covers page 8 of Notes 2 from Calc C, and this is where we start to talk about the error involved in Taylor polynomials. And this is kind of a big topic. A lot of people find it challenging because there's kind of a lot going on. So I'm going to do my best to kind of illuminate what's happening. So first of all, you need to know everything that's in this box. So it's called the Lagrange error bound for an nth degree Taylor polynomial. So if we use the nth degree Taylor polynomial, which keep in mind, to get the nth degree polynomial, you have to take derivatives up to the nth derivative. So that's going to be key here when we look at the error. So we've taken up to, so if it's fifth degree Taylor polynomial, we've taken 5 derivatives. So that's really important. So using the nth degree Taylor polynomial centered at x equals a to approximate a function gives a maximum error of the so it's the absolute value of the error, because you might be over, you might be under, we don't really know, is less than or equal to m, which I think is called m because it's mysterious. Probably not, but it's kind of mysterious. So let's see, it's m times the absolute value of x minus a to the n plus 1 all over n plus 1 factorial. So a lot going on there. So you're going to memorize that like right now. But it's not that hard to memorize, actually. And the reason is because if you think of the nth term of a Taylor polynomial, it's the nth derivative at a, x minus a to the n over n factorial. So this thing in the box here, it looks an awful lot like just kind of the first term that you left off. Like if you were to have written one more term of your Taylor polynomial, it would look an awful lot like this error. And that's good because it makes it so much easier to remember. But what I do want to highlight is m has so much going on. So it's the maximum of the absolute value of the n plus first derivative. So remember, if you wrote a 7th degree Taylor polynomial, you would take, you'd make your table, you'd go to the 7th derivative. So what you would actually need in that case is you would need the 8th derivative. You need to go one more than what you needed to write your polynomial. So we would go to the 8th derivative if we had written a 7th degree. So it's the n plus first derivative on the interval with endpoints x and a. So a is obviously the center. I mean, that's just kind of given. This x here confuses people a little bit, but x is actually just the value at which you're approximating the function. So usually when you write a Taylor polynomial, certainly for Calc BC, you're writing it so that you can then plug something in, right? So if the problem said to approximate f of 3.1, then 3.1 would actually be the value of x in this kind of definition here. So it's not that hard once you get used to it, but we do need to kind of look at it. So finding m is by far the hardest part of this once you've got everything memorized. So I'm going to put finding in quotes because what ends up happening is that for the most part we can't really find m. So what we do is we're either just kind of given it, which actually happens almost all the time on the AP exam, which is really nice. I think that if you had to grade like 100,000 tests and people were coming up with various values for m, it would drive you nuts, so you also would probably just give the value of m, but it's a little hidden, and we'll maybe look at some of those ways. Sometimes we just make a super convenient choice. In fact, almost always we make a super convenient choice. So, for example, E is often involved, and E is like 2.718. That's less than 3. 3 is the most convenient number that we could use to approximate E, because we have to go over, otherwise our error estimate could be too low. So E is definitely less than 3, so sometimes if E is involved, we'll just use 3. If sine or cosine are involved, we use the fact that the absolute value of sine is always less than or equal to 1, and the same for cosine. So we make some very convenient choices. So now let's take a look at an example. So this example is, it's not that easy. And after this, we'll do some easier problems, not in this video, because this video will run a little long, I think. But we have f of x is e to the 3x. We want to center our polynomial at 0. We want to approximate f of 0.25 using a third degree Taylor polynomial, which is also called Maclaurin because you're centered at 0. So what I've done is I actually have this particular Taylor polynomial memorized, and you will too soon. So just kind of write it out. So this is the polynomial. So if I want to approximate f of 0.25, what I do is just plug 0.25 into this. And that is a calculator problem. So I punched it in, and I got this. So I'm claiming that e to the 0.75, which is 3 times 0.25, is really close to 2.1015625. So that's my claim. But now the question is, like, how wrong could that possibly be? And it turns out we can figure it out. But what we need to do is we need to figure out the error. So if you think about it, I'm going to go back. I'm like going backwards here. I would make my table, and to write the third degree polynomial, I would need the 0th, first, second, and third derivatives. So I need up to 3 to make my polynomial. So what I do when I'm doing problems involving error is I draw a little line in my table and I add the next derivative. So in this case, it'll be the 4th derivative. So let me just fill in. So that's n is 3 in this context. So n plus 1 would be 4. And that's good because now I know what to plug into my formula for the error. So here are some derivatives. Okay, so now I'm ready to start trying to figure out what m is. So remember I said we only kind of find m, and usually what we do is put a bound on m, actually. So the 4th derivative is 3 to the 4th e to the 3x. So m is going to be the maximum of the absolute value of the 4th derivative on the interval from 0 to 0.25. And now where did 0 and 0.25 come from? 0 is a, that's the center, and then 0.25 is the value that I'm plugging into the function. So that's what I'm actually looking for. So the actual value of m can be found. E to the 3x definitely increases on that interval. It increases everywhere. So if a function is increasing, it will have its maximum at the right endpoint. So I actually know the exact value of m, but there's something weird about knowing the exact value of m here. So m is actually 3 to the 4th e to the 0.75. But if you think about it, this e to the 0.75 is actually what I'm approximating. So if I knew that value, what would be the point of approximating this whole thing? So I need to do something else. So here's what I'm going to do. I'm going to trap m under something, basically. So 3 to the 4th stays. I'm going to, instead of using e, I'm going to use 3 because e is less than 3. And then instead of using 0.25, I'm going to use 1/3 because 1/3 is bigger than 0.25. So what I've done is I've made sure all the inequalities work out so that I'm guaranteeing to get a number bigger than the actual value of m. And if I simplify this, I get that m is definitely less than 3 to the 5th. So I'm going to use 3 to the 5th. You could do better because e is 2.718. You could use 2.8, let's say, instead of using 3, and then your error would be smaller, and that's usually better, but we're going with the convenient choice here. Okay, so the absolute value of the error, less than or equal to m, but in this case I'm using a bound for m, so 3 to the 5th. The absolute value of, and now it's x, which is 0.25, minus a, which is the center, which is 0, to the n plus 1, but I already know that n plus 1 is 4. Using that table is really helpful in this context. To the 4th over 4 factorial, definitely a calculator type thing here. So I get the absolute value of the error is less than or equal to 0.039551, which is pretty small, right? Like 0.04-ish. You're not very far off. And then one of the things that we can do that's kind of a good idea is you can write a range of values. So the true value, f of 0.25, is actually between my approximation minus my error and my approximation plus my error. And if you grab a calculator and kind of punch all that in, you'll see that it actually does fall in that interval. So that's a first example. It's a challenging example too. I think it's good to start out with something that really makes you think. And in the next video, I'll do 1 or 2 additional things and then probably just write out the answers to a bunch of other problems so you can kind of pause the video and look at that. But anyway, I hope you found this helpful, and good luck.